Assalamualaikum warahmatullahi wabarakatuh. For this project, our team of four was required to design and build a 3D truss bridge. The bridge used interconnected triangular structure to achieve a high strength to weight ratio. The material allows for this project we are only brass wood or ice cream stick and glue. Next, the bridge was required to support a 10 kilogram dead load suspend exactly at the center. In addition, the bridge has to have a clear span of 100 centimeters and a total length of the lace 104 centimeters to provide a secure overlap at the both ends. Finally, the bridge across a section had to fit within the specified dimension of 10 centimeters by 10 centimeters. So, for the problem statement, this project focused on designing a lightweight but strong bridge using balsa wood. One of the main challenges is that the traditional heavy material increase cost and reduce structural efficiency. Another challenge is the variability of balsa wood properties as its strength can change depending on the grain orientation, making the structure less predictable. So, in addition, balsa wood is prone to failure under axial compression and joint shear stress, which can affect the bridge performance. Therefore, our main objective is to optimize the bridge design so that it can support a 10 kilogram load while remaining lightweight and structural stable.
This slide presents the objective of our Warren Truss Bridge project. The first objective is to design and construct an optimized 3D Warren Truss Bridge with a span of 100 centimeters and a cross section of 10 by 10 centimeters using balsa wood and ice cream stick. The second objective is to calculate the internal axial force when a 10 kilogram load is applied at the center of the bridge. We will compare the theoretical calculation with the actual result obtained from physical testing. The third objective is to maximize the load to weight ratio by improving joint strength and enhancing the structural bracing of the bridge. Finally, we aim to ensure effective teamwork and timely project completion through proper planning, the use of Gantt chart, and regular weekly meeting. This objective will help us develop a bridge that is strong, efficient, and capable of meeting the project requirement. Next, I will brief review our project. This project used a Warren truss bridge design with a span of 100 centimeters. The bridge was chosen because its triangular structure had to distribute load efficiently and improve overall stability. The bridge is designed to support a 10 kilogram central load by utilizing a axial force in its member, where some members experience tension while others experience compression. To achieve a high strength and to weight ratio, we use a combination of balsa wood and ice cream stick. These materials are lightweight, cost effective, and suitable for testing structural performance. Overall, the design aims to create a bridge that is strong, stable, and efficient while meeting all project requirements. Thank you.
Next, for material and joint strategy. For hybrid design, we use balsa for strength to weight efficiency in tension, while denser, stiff ice cream wood and less compressive load. For joint optimization, it can prevent common failure such as joint shear or member buckling at high modulus adhesive, and it must be applied uniformly across all lap joints. For structural priority, it can maximizing joint surface area is essential to ensure load capacity without significantly increase the bridge dead weight.
For theoretical concepts, number one is truss theory. The Warden truss designed to convert external loads into internal axial force, tension, and compression to minimize the bending moments. Number two is statics. The application of the methods of joints to achieve static equilibrium and calculate internal forces within each member. And number three is material mechanics. To optimize of material properties, balsa for tensile strength and ice cream wood for compressive stiffness to achieve high load to weight efficiency.
Next, for theoretical concept, first the structure stability. We add lateral cross bracing to the side of the structure, which is successfully prevent it from buckling, bending, or twisting when a heavy load is applied. For joint mechanic, we use high strength adhesive and maximize the overlapping surface area of the joint so that the connection point can resist the strong force and won't break apart. For load to weight optimization, we identify and remove all the redundant zero force member from the design, which make the overall structure much lighter while still maintaining its full strength.
For methodology, number one is to develop a 100 span Warren truss by performing method of joints calculation to identify critical members and predict load distribution. And number two is fabrication to construct the bridge using balsa and ice cream sticks. But for our project, we use ice cream sticks to employing lap joints for strength and cross bracing for lateral stability. And number three is quality control. Utilize precision cutting and clamping during curing to ensure structural alignment. And number four is testing. Evaluate structural efficiency by applying a 10 kilo central load across the 100 cm span to compare actual performance with a theoretical calculation.
So this slide show our CAD design of the 3D truss bridge. We use CAD software to model the bridge and verify its dimension before construction. The triangular truss structure was chosen to improve strength, stability, and load distribution.
Now, I will explain the calculation process used in this project. First, we list all the parameters involved, such as the bridge dimension, material properties, and the applied load. These values are important for ensuring accurate analysis. Now, we calculate the support reaction using the equilibrium equation. This allows us to determine how the external load is distributed to the support. After that, The method of joint is used to calculate the internal force in each truss member. Through this method, we can identify whether a member is under tension or compression. Finally, the method of section is applied to determine the maximum cord stress at the midspan of the bridge. This helps us identify the critical members and evaluate the overall structural performance. This calculation provide the theoretical result, which are later compared with the actual testing result of the bridge. After completing the calculation, we can now discuss the finding and evaluate the performance of our Warren Truss Bridge design.
Next, for discussion for our project, the bridge is successfully sustained the 10 kg load with minimal deflection, confirming that the Warren truss design efficiently translated theoretically axial force model into real-world performance. While minor discrepancies occur due to the material variability and fabrication tolerance, the project demonstrates that combining rigorous structure analysis with precise craftsmanship is essential for maximizing load to weight efficiency.
So, in conclusion, the project successfully validated the effectiveness of the Warren Truss design in supporting the 10 kilolog through efficient axial force distribution, with minimal deformation confirming the accuracy of both the structural analysis and fabrication techniques. This appearance provided practical insights into a load-bearing behavior and the critical role of joint integrity and member stability in optimizing structural performance.